Well, let's work through our test review. On this first page, we've got several integral questions. And before we get into those, I just want to review quickly. When you have integrals just like these where you're just straight up calculating an integral, you really have three choices about how to do it. Well, four choices really. Your first choice is just to apply integral rules directly. But if an integral rule can't be applied, then we have to do one of three things. One possibility is to use U substitution. And U substitution is going to work when you have a composite function where the inside function, its derivative is somewhere else there in the integrand, in the expression that we're trying to integrate. Another thing that we can do is algebraic manipulation. Sometimes we can just apply some algebra and get the expression in a form where we can apply our integral rules. And finally, sometimes a good strategy is just to sketch a graph and find the area. And so a lot of times if you have like a linear function or something like that, it may just be quicker to sketch a quick graph and then find the area of it. So for calculating integrals, these are really your three choices. If you can't just apply an integral rule directly, then we have to do one of these three things to get the expression in a form that we can integrate. So I'm going to erase that and let's look at this first problem. I have the integral of x over x squared plus 1. There's really no algebraic manipulation that I can do to that to simplify, and so I'm going to try U substitution. And for my U, I'm going to choose x squared plus 1, and the reason that I'm choosing that is because it has the higher exponent. When I do the derivative of x squared plus 1, I'm going to get 2x, and that's the x is what I have there in the numerator. So I'm going to let U equal x squared plus 1. So du is going to be 2x dx. Now up here in my integral, I have x dx. I don't have that 2 that I need. So I'm going to multiply in the 2, but if I do that, I need to also multiply a 1/2 on the outside to balance it out so that I don't change the value of the integral. So now I'm ready to rewrite this integral as 1/2 times the integral. And let me do this down here, that's my U, and then all of this together is the du. So what I have ended up with is just 1 over U du. Now in my original integral, the limits on my integral were 2 and 3. Those numbers are x numbers, but now I've changed my integral to be in terms of U. And so I need to change my limits to be in terms of U as well. So I'm going to go down here to our U equation. U is equal to x squared plus 1. So when x equals 2, which is my lower limit, then U equals 2 squared plus 1, or 5. And so I'm going to put that, my lower limit is now 5. And when x equals 3, U is going to be 3 squared plus 1, or 10. And so my upper limit on my integral is 10. So now I'm ready to integrate. The 1/2 is just going to stay out front, and the integral of 1 over U is, of course, the natural log of the absolute value of U. And we want to evaluate that from 5 to 10. So if I substitute in applying the fundamental theorem of calculus, I'm going to keep the 1/2 out in front. I'm going to substitute the 10 first, natural log of 10 minus the natural log of 5. So I seem to have an answer here, but when I look at my answer choices, none of those match what I have. They're all single log expressions. And so I need to remember my log properties here. When I'm subtracting logs, remember that logs are exponents. And if you are subtracting exponents, then what are you doing? you must be dividing. So I'm going to head down here, and I'm going to rewrite this as 1/2 times the natural log of 10 divided by 5, which of course is the 1/2 of the natural log of 2. Whoop, wrong answer, sorry. We'll answer B. Let's move on to the next question. Here we go, question number 2. Now this is going to be one of those times where I think sketching a graph and finding area is going to definitely be the easiest way to go. We don't have an integral rule that involves absolute value. And the problem with absolute value is it makes areas that would normally be negative in the graph and makes them positive. And so it makes calculating the integral a bit of a challenge. But if I sketch this graph, of course it's going to be the absolute value graph shifted to the right 1 unit. So it would look something like this. I want to integrate from 0 to 3. So I need to find this area plus this area. So let's start with that small triangle first. The base of this triangle is 1, and the height of that triangle is also 1. If I substitute 0 into the integral, 0 minus 1 is -1, and the absolute value of -1 is 1. So that means this point right here, this point is 1, and that's 1. So that triangle, the area of that triangle is 1/2, plus the area of this other triangle. Of course, we're going out to 3, so that makes my base equal to 2. And then if you're not sure what this point is up here, just substitute 3 into your function. 3 minus 1 is 2, and the absolute value of 2 is, of course, 2. So this is the point 3, 2, which means that this side of the triangle is also 2. So 2 times 2 is 4, and half of 4 is 2. And I get 1/2 plus 2, which is equal to 5/2. Let's move on to the next question. Now this question, you might try U substitution first, and I don't think it's a bad start. Let's see what happens if we do that. If I let U equal x squared minus 1, and then I do du, that du would be equal to 2x. But notice down here in the denominator, I don't just have an x, I have an x plus 1. I have this extra plus 1 here. That means that the U substitution is not going to work, and we have to do something else. So my other options are to sketch a graph and find area. I probably don't want to sketch that graph. My last choice is algebraic manipulation, and that's going to be our best choice here because my numerator factors into x plus 1 times x minus 1. I have x plus 1 on the denominator, and so the x plus 1's cancel out. And so really I'm just integrating x minus 1 from 1 to 2. The integral of x is x squared over 2 minus the integral of 1, which would be 1x or just x. And my limits are 1 to 2. So now I'm going to apply fundamental theorem of calculus. I'm going to substitute in the top number, 2 squared over 2 minus 2 minus, and then I'm going to substitute in the bottom number, 1 squared over 2 minus 1. And in this first parentheses, I get 4 over 2 minus 2, which of course is 2 minus 2 or 0. And then over here, I get 1/2 minus 1, which would be negative 1/2, and minus a negative 1/2 would give me positive 1/2. And so my answer is answer A. Question number 4. Pretty scary looking integral here, but we only have 3 choices. I'm obviously not going to sketch a graph. There's not any algebraic manipulation I can do. I'm left with U substitution as my only option. And remember that your u is usually going to be some inside function of a composite function. In this case, the tangent x is an inside function of e raised to a power. And so I'm going to make that my u. U is equal to tangent x. And if my u is tangent x, the derivative of tangent x is secant squared x, which hopefully you recognize is equal to 1 over cosine squared x. And that's fantastic because that's what I have here in my integral is 1 over cosine squared x. Whoops, I forgot my dx, didn't I? We'll squeeze it in there, and dx right here. So this tangent is my u, and if I put a 1 there just as a placeholder, 1 over cosine squared dx, that's my du. So I'm going to rewrite this integral as e to the u du. Now I've changed from x's to u's. My limits on the integral are x numbers, 0 to pi over 4. I need to change them to be u numbers, and so I'm going to substitute them into my u equation. If x is 0, I'll do this out here on the side. If x is equal to 0, then tangent x is going to be equal to the tangent at 0. And remember, tangent is sine over cosine. Sine of 0 is 0. So tangent at 0 is also 0. So that's going to be my lower limit. And then if x is pi over 4, tangent of pi over 4 is equal to, again, sine over cosine. Sine of pi over 4 is square root of 2 over 2. Cosine of pi over 4 is square root of 2 over 2. And so square root of 2 over 2 over square root of 2 over 2 would just be 1. So tangent of pi over 4 is 1, and that becomes my upper limit. So now I'm ready to take an integral. The integral of e to the u is, of course, just e to the u from 0 to 1. And fundamental theorem of calculus, I'm going to substitute in the top number, e to the 1, minus, substitute in the bottom number, e to the 0. And e to the 1 is e to the 0 is 1. And so we end up with answer C. Let's move on to number 5. If the integral from 0 to k of 2kx minus x squared dx equals 18, then what does k equal? Well, this problem may seem like you look at it and you're like, well, I don't know how to do that, but let's just integrate. K is just a constant, and so when I integrate 2kx, the 2 and the k are just going to stay, and I'm going to integrate x, which of course would be x squared over 2, minus the integral of x squared, which would be x cubed over 3, and I'm going to evaluate that from 0 to k. And whenever I do that, they're telling me that this should be equal to 18. So now we're going to apply the fundamental theorem of calculus. Actually, notice here these 2's, I can cancel those out. That makes it a little bit simpler for us. If I plug in, now to do fundamental theorem of calculus, I'm going to plug in the top number first. So I get k times k squared minus k cubed over 3. Minus, and then I'm going to substitute in the 0. Well, of course, that's just going to give me 0 in both of those. And this is equal to 18. So what I have here, k times k squared would be k cubed minus k cubed over 3 equals 18. I need to get a common denominator. And so I'm just going to make this 1k cubed into 3 over 3 k cubed. And so I have 3k cubed minus k cubed, both over 3. So that's going to give me 2/3 k cubed equal to 18. And That means 2k cubed is equal to 54 if I multiply by 3. And then divide by 2, and k cubed equals 27. And so, of course, k would be equal to 3. If I cube root both sides, I get k equal to 3. Answer C. Question number 6. If the second derivative of f is given by 2x minus cosine x, which of the following could be f of x? So in this problem we have a second derivative, and they're asking us to get back to the original function. So what that means is that I need to integrate twice. So my first derivative is going to be equal to the integral of 2x minus cosine x. And if I integrate 2x, I'm going to get 2x squared over 2 and minus the integral of cosine, which is sine x. And then since this is an indefinite integral, I don't have limits on my integral, I need to put plus c. My 2's cancel out here, and so I'm just left with x squared minus sine x plus c. That gives me the first derivative, but they're asking us what f is equal to. So f is going to be the integral of x squared minus sine x plus c dx. And if I do that integral, the integral of x squared is going to be x cubed over 3 minus the integral of sine is negative cosine x plus the integral of c, which of course is just a constant, is going to be that constant times x. And then this is still an indefinite integral, and so I need to add another constant at the end. I'm going to call it c sub 1 to differentiate it from the original constant that I got in the previous integral. So what I have here is x cubed over 3 plus cosine x plus some constant times x plus some other constant. And so that answer matches answer A. Let's move on to number 7. Number 7, the graph of f is shown in the figure above. If g equals the integral from a to x of f, for what value of x does g have a maximum? So before we even try to answer this question, there's a couple things that I want you to do for annotation. First of all, they said this is the graph of f, and so we need to be sure that we realize what we're looking at here is f. Now, whenever we have a function defined by an integral like this, I want us to do this kind of annotation. So g is equal to the integral of f, which in this case is going to mean that g is the area of what we're looking for, of what we're looking at, because what we're looking at here again is f. G prime would be equal to the derivative of the integral of f, and of course the derivative and the integral just cancel out, and I'm left with f, which is our actual graph that we're looking at. And then g double prime would be f prime, which would be the slope of the graph that we're looking at. Now our question says, for what value of x does g have a maximum? So there's another flashcard, and I want you to annotate that. If g has a maximum, then that means that g prime changes from positive to 0 to negative. So now let's see if we can figure out the answer to this question. Okay, there we go. Sorry, I lost it for a second. We want g prime to go from positive to 0 to negative, and notice in our annotations up here we said that g prime is equal to the graph that we're looking at. So all I'm looking for is, where is my graph going from positive to 0 to negative? And that happens right here at C, positive, 0, negative. And so my answer is choice C. Question 8. Which of the following represents the area of the shaded region in the figure above? Well, if I look at that figure and notice it says area, and this is area not between a function and the x-axis, but between two different functions. And so, of course, the formula that I'm wanting you to remember here is top minus bottom. Area is equal to top minus bottom. And in this case, the top of that area is D, and the bottom of that area is f of x. So D minus f of x, top minus bottom. And then the limits on my integral, they should both be x numbers, and that shaded region starts at the x value of a and ends at the x value of b. And so that makes my answer choice B. All right, question number 9. The region enclosed by the graph of y equals x squared, the line x equals 2, and the x-axis is revolved about the y-axis. The volume of the solid generated is, so we're looking for volume, a solid of revolution. Not sure if it's disk or washer yet. We need to sketch this graph. So y equals x squared. Wow, that's not the best graph. Let's try again. Y equals x squared. The line x equals 2. So let's say that's 2. And the x-axis. Okay, so my region that I'm interested in here is this region right here. And we're going to revolve that region around the y-axis. So that means, I didn't really leave myself enough room to reflect it, but that means that we're going to end up with something like this, kind of a bowl with a straight bottom and straight edges. So I do have a hole here. That means this is the washer method. And so I'm going to go ahead and write down the formula. Integral from a to b of pi times big R squared minus little r squared. And then notice that we are rotating around the y-axis, revolved about the y-axis. And so that means that I have a vertical axis, which means that my integral needs to be dy. And so that means that my functions need to be in terms of y. Now I only have one function here, which was y equals x squared. And so if I solve that for x is going to be equal to the square root of y. And we don't have to worry about the negative version because we are obviously dealing with the piece that's in the first quadrant. So that's the positive piece of the square root of y. So now the other thing I need to figure out is what's my big R and what's my little r. So I'm going to draw in those representative rectangles from the axis all the way out to the edge of the solid, and then from the axis to the edge of the hole. This is my big R and this is my little r. So hopefully you can see that the big R is going all the way out to 2, and it's just remaining 2. So this is going to be equal to the integral pi times the big R, which is just 2, minus the little r, which as you can see is just the distance from the y-axis to the function. And so that's just going to be the function square root of y squared dy. Now my limits a and b, because my integral is in terms of y, those limits need to be y values as well. And so this one we're going to have to figure out. But let's go back to, we have this vertical line at x equals 2, which means that the top of my solid is right here. And the coordinates of that point would of course be 2, 4, because it's y equals x squared. And if x is 2, then x squared would be 4. So my solid is going from 0 up to 4. 0 to 4. All right, so now we're ready to integrate and find our answer. This is, let's see, let's go over here. This is going to be equal to the integral from 0 to 4 of pi times 4 minus y dy. If I simplify that, 2 squared is 4, square root of y squared is y. And so now let's do the integral. Pi is just going to stay here. The integral of 4 is going to be 4y minus the integral of y squared over 2. And we need to evaluate from 0 to 4. Those are our limits. So if I substitute in the 4, I get 16. 4 times 4 is 16 minus 4 squared over 2 minus, sorry, let me put a bracket in here. We're going to multiply this pi times the whole thing. If I substitute in 0, fortunately I get 0. So pi times 4 squared is 16, divided by 2 is 8. So this is 16 minus 8, which is 8 pi. And so our answer is answer choice A. We've got one more multiple choice question. The base of a solid is the region in the first quadrant enclosed by the parabola y equals 4x squared, the line x equals 1, and the x-axis. Each plane section of the solid perpendicular to the x-axis is a square. What is the volume? So this is where we've got cross-sections, known cross-sections, different. We don't have cylinders from rotation, but we're slicing the volume into shapes that we're familiar with. Let's sketch our region. 4x squared is going to look like that. X equals 1 is, of course, a vertical line, and the x-axis. So this is very similar to the previous region that we had. Let's go ahead and find the coordinates of this point, because we're probably going to need those. My x-coordinate is 1, and the y-coordinate, of course, would be 4. If I substitute 1 into 4x squared, we get 4. Now, our cross sections are going to be squares, and they're going to be perpendicular to the x-axis. So this would be representative of the sides of the squares that I'm looking at. Now my volume formula, whenever we have these cross sections, we're going to integrate from A to B the area of the base dx, because I do have a horizontal axis here that we're perpendicular to the x-axis. In this case, since my bases are squares, my shapes are squares, we're going to do side squared dx. And my limits are going to be x numbers, since my integral is in terms of x. And so I'm going from 0 to 1. So now I need to figure out how long the side of a square is. And remember, when I say how long, we should typically be thinking top minus bottom. The bottom here is just the x-axis. So top minus bottom is really just going to be the function, 4x squared. So that's the length of a side of a square. And we're going to square it to get the area of that square. And then multiply by the height dx to get the volume. So I'm going to go ahead and square 4x squared to get 16x to the 4th dx, and now we are ready to integrate. So it would be equal to 16x to the 5th over 5 from 0 to 1. And I'm going to plug in 1 first, minus, and plug in 0. That, of course, would be 0. And so my final answer here is 16/5, which gives us answer D. All right, I'm going to stop here and put the FRQs on a separate video.